All right, this is the final part of problem 103. So we've computed all the reaction forces. We sized element BC, and the only thing left to do is size the pins at B and A for shear failure. All right, and again, we're going to assume it's the same diameter pin. So we have to check for the shear stress, the maximum shear stress at both pins, and then pick the largest diameter, basically. Or the other way to think about it is we look at which case gives us the maximum shear stress and size both pins accordingly. Okay, you could assume that the book is asking for a diameter at pin A and a diameter at pin B. I'm actually not entirely sure which it is. If I were so lazy, I could probably check in the solution manual, but let's make that assumption, all right? Okay, so I want to talk a little bit about the shear and the pins. Again, we'll see the difference here. So pin A has one shearing plane, so it's what's called single shear. And then you look at the pin at B, it shears along two planes, all right? So let's first look at A. A is a little simpler, and then you'll see how the double shear case actually drops is able to do a better job of sustaining the shear loading than the single shear case. All right? Okay. Let's put this to the side. Oops. So let me zoom out. Zoom out. Zoom out. Zoom in. Zoom in. One more. A little bit more. There you go. All right. So there we are. So let's look closely at pin A. All right. So I'm going to draw a side view. This is pin A. And then also kind of a top view. I guess we should say a bottom view. All right. So let's first look at the top view. So, here's the reaction bracket, and then here's the element AB acting off to this way. So if we look at the bracket, I'm doing this, you might immediately see that the reaction force that acts at A actually transmits onto the pin directly. But let's go through a slower step. If I look at the bracket here, that's sort of at A, here's point A, we know there's an X reaction force here at A, and we computed that to be minus 4.67 kips. And then we also had a Y reaction force at A, and that was equal to 8 kips. All right. If you look at sum of forces on this bracket, right, the reaction forces from pin A act at A, and they have to balance it. So that means you actually have an equal and opposite reaction forces from the pin. So here's the reaction from the pin at A in the X direction, and the reaction from the pin in the Y direction. So, right, they're acting on each other, all right? So they have to balance out, okay? And they're all acting at A, so there is no opportunity for any moments to manifest themselves, all right? All right. So if we look at pin A, right, we have the reaction components. This is the bracket acting on A. Okay? So this is the minus 4.67, and this is the 8 kip. All right. So if we looked at the bracket, those actually act on this bottom view. The bracket kind of is over on this lower side, so these guys act this way and into the board. All right. Now the pin, or actually exerting on the pin, okay. Also acting on the pin are the reactions or the contact forces from member AB. All right. Again, those are going to have to balance out. So this would be the reaction in the y direction from element AB. It's going to have to equal this in the opposite direction, and then here is the reaction force from element AB onto the pin in the x direction, and that's going to be minus 4.67, acting the opposite direction, kips. All right. Another way you can look at it is if I look at this reaction force, it has a magnitude of direction. It has a line of action, right? And it's roughly, well, I shouldn't try to draw it, but if this leg is the minus 4.67 and this leg is the 8 kips, this is the net reaction force at pin A. Okay? That's coming from this bracket. There's an equal and opposite from element AB that acts on it. Okay? I have a tough time always drawing those. Probably easier if I draw it in 3D. So this is the reaction force, net reaction force from the bracket onto the pin. And then this is the net reaction force from member AB onto the pin. Okay, and again, everything is assumed to go through the section, so there's no way you can have offset moments to go on, so they have to be equal and opposite. All right? So if we're to try to draw it more like in 3D, here's the pin A, right? We have a reaction here on this. This is the reaction from the bracket onto the pin. That's a force. And then on this side, actually equal and opposite, but offset by this distance, is the reaction force on the pin from AB. Okay? That doesn't look much better, right? But you have to imagine acting on the pin. Maybe it's better if I do it with a pen, right? So imagine this is pin AB. Okay? Let's see if I can do this. All right? The bracket acts on pin AB at this point with a reaction force this way. Down the shaft, there's an equal and opposite, which is member AB on the pin. So the shear area is through the cross section. Okay? All right. So we're going to have to figure out the net component of this anyway. So this here, the magnitude of this is going to be the sum of these components squared. You can see the fact that this is a negative really doesn't matter. So this magnitude here is the square root of 4.67 squared plus 8 squared. So that total shear force acting on the pin is going to be plus square root. This is 9.26 kip, and I guess I should have known that would be the actual same force at C. Okay, so if you look at the pin, this is the one that has the cross-sectional area of the pin Let's draw it. Say we take a cut here, and now we're looking at this side. So acting on this, we have the reaction force from AB onto it, and it has a value of 9.26 kips. And that means the shear through this cross-section has to also equal 9.26 kips, but acting in the opposite direction. So the net forces is 0. Yeah, there's a little moment actually acting on the pin as well, but you know, we tend to kind of ignore those in this class, all right? But there is a little moment due to the fact that these guys are offset by this little distance, okay? D, all right? But let's ignore that for now, all right? So these guys are equal and opposite. What I'm saying is there's basically has to be a little moment here as well. When we talk about beam bending, we might consider those. All right. Okay, so that's a lot to it. Maybe I didn't do a great job of explaining that clearly, but you should go back and try to conceptualize that. Okay, so now we know the shear force in the pin A. We can go through and figure out what the diameter should be. So this is not the diameter. So the average shear stress through the pin is going to be, put the A here. The shear force at pin A over the cross-sectional area at A. And now this cross-sectional area is the one that involves the diameter, right? So this is the pi on 4 diameter of pin A squared. And we know this quantity here has to be less than or equal to the allowable, which is the 10 KSI. So we'll pick the limiting case where it's equal to and figure out the maximum, the minimum area or the minimum diameter that makes this work out. All right, so rearranging this is the, so we have the diameter at A squared equals the shear force at A over 4 pi, flipping that around, and then this becomes tau allowable. Okay? So we can do the units on this. This is force per area. This is force. This is force per area. So it basically puts inches squared on top so we get consistent units. I guess you want to get the D exactly. We would take the square root of this quantity. All right, so that's the square root of 4 times V, which is 9.26 kips, over pi times tau allowable, which is 10 KSI. The K's cancel out, the pounds cancel out, so I just get inches squared, square root gives me inches, so that equals, doing the math, 4 times 9.26 is 37. Let's divide that by pi. And let's divide that then by 10. And then we take the square root of 1.17. And that gives me 1.08 inches. Okay, so the diameter of the pin there has to be 1 inch. All right, let's go look at pin BC, and I'll be a little quicker on this one. So let's consider. Let's consider the pin at B. All right, it's going to go the same way. Without getting so long-winded about it, you're going to have a net reaction force acting on pin B, and then there's going to be an equal opposite from the other element acting on it. So if we go back and look at this, this one's kind of in double shear. So if here is pin B, looked at the top, right, you will get a force through the ends. All right? And then a force through the middle. So these guys are the force acting on pin B from element AB. All right? So I'm going to call that and this is the shear force from element CB. Okay? Now since element CB I'm drawing the dashed line is actually kind of like the knuckle. Okay? And now this is actually looking at the direction of line of force. So we actually know from looking at this that this line of force, reaction C, is acting at tension that way. So actually when we're looking at this, we're kind of looking at this view. All right? So when I draw that, I'm actually looking down this way. So for a little eyeball. All right? Looking down that way. So you can see, well, I guess that would be the other way. So you can see the reaction force from C going this way, and then the two reaction forces from the knuckle from AB going down. So you have to imagine this is actually. Well, let me just redraw it. So if we look at this view, this is view AA. So we look at view AA at the pin. Let's see if I can get this right this time. So here we have the reaction force acting from element CB. This is RC. Okay, we know that's RC. That's equal to the 9.24 KSI. So this is the force from BC onto pin B. Okay, that's that reaction force. Now let me do a different color. I can stand that a little better. Right. So that's that element in green, BC. All right. Now, AB has this sort of knuckle shape going around the pin. Okay. Looks like this somehow. Okay. So it exerts, assuming it's distributed evenly, half the force here and half the force here. Okay? So this is actually going to be RC over 2, and this is going to be RC over 2. All right? This is actually the reaction. This is the force, or I should say this is 1/2 of the force of element AB onto pin B. Okay, so again, we're kind of looking down this view. So if you look down this view, you have, let me rotate this a little better. Right, we know that element BC is a tension, and its magnitude is 9.27. So it's pulling this way. That means that element AB has to act in the equal and opposite direction, but since it's a knuckle joint here, it actually splits that force in half, a half at the bottom and a half at the top. Okay? Total force in this direction sums to 0, right? This is the line BC. Looking down. Okay, sometimes I wonder if I explain those well or not. Sometimes I think I get a little too much into it. Okay. Now again, we have two shear areas that this is acting on. Double shear, right? This is double shear. Oops. All right. So you'll actually, we did a double shear problem before. You see, you actually will get the same stress on both areas. So the nice thing about the double shear, if this were in single shear, right, you would see that this force here would actually be RC. It would be equal and opposite, like at pin A. And then you would have the entire force at RC acting over this area. When it's in double shear, you get half. Okay, so let's look at this middle section. This will kind of help a little bit. So if we look at the middle section, all right, that's what's here. All right, we have the RC acting in this direction, and that's the 9.24. What do I have KSI? Kips. Kips. And then here are the two shear forces. They have to be equal. If they're not equal, the sum of moments won't work out. And you can see that. If this one is a little bigger than this one, you did sum of moments around this point, it would tend to rotate. So they have to be equal from sum of moments. So they both have to be V, and you can sum them up, and you can see that V equals RC on 2. So it's half of this force. If it were single shear, you would have a moment arising that would also kind of torque the bolt a little bit, bend the bolt, and then the entire force RC would be acting on this shear area. All right? So, well, okay, let's do the stress analysis on this area. So the stress, the average shear stress here is that V over the area, okay, and that has to be less than or equal to the 10 KSI. So this equation goes the same as pin A. So basically, but now we're at B, the diameter, well, right, this area is pi on 4 times the diameter at B squared. So the diameter at B is the square root of 4 times the V at pin B over pi times the allowable, right? This is tau allowable. All right, so that is 4 times the reaction force V is half of this, so that's the 4.674 kips. 4.74 kips over pi, and then the tau allowable is the 10 KSI. Again, the 10 to the third terms drops out, pounds drop out. I get inch squared, take the square root, that becomes inches, and so that comes out to be 4.74 times 3.14156 divide the 10 divide. So that gives me 0.60 inches. All right, so that is less than the 1.08 inches for pin A. So in fact, this diameter is the limiting diameter, so it should be 1.08. Pins probably don't come in something like that, so you'd probably have to get maybe like a 1 1/8 diameter pin, okay? Just because you probably can't get the pin exactly to that size. So 1 1/8 will give you a little extra margin of safety on there. Okay? Sorry for drawing the shear on the pins in a little confused manner, but if you think about it, you know, let me just say it one more time, and hopefully it makes a little more sense. Right? The pin, right? If here's the cross section of the pin, you know, whatever force is acting from one member has to be balanced by the force acting on the other member. You know, they can't be at an angle, otherwise that'll induce a rotation. All right, it's not going to be in equilibrium. Now, in this case here, for the double shear, right, we're looking along this line AA. All right? And that's this what we drew here. So we got the force acting on the pin down the middle of the pin from element BC, and then equal and opposite and split in half because it was a double shear is the force from element AB acting on the pin B. Okay? Same concept at pin A, except it's in single shear, not double shear. All right? So double shear carries the load a little better than the single shear. All right? Okay.